So that this is the topic of the talk, and it's actually very befitting for this conference in honor of John Harnad, because actually, you see, I've also just, Misha told me that I use these SAT words, right? Years of cogitations. We really thought hard about this problem. And how many years, you may ask? Let's say 18, 20?
Well, 2004.
2004, 18.
I started breaking about 10 years before. When we started working together, it was 2000.
Yeah, so actually, I will start a little bit with my reminiscences, right? And then we get to the talk. So I've known John for 23 years, because when I was in my last year of PhD, I went to MSRI. There was a semester on random matrices. Actually, many people probably started interacting with John at that talk, at that semester. And I actually coincidentally had applied to MSRI, to CRM ISM postdocs. And at that time, there was a piano in the lobby at MSRI. You know, it's an open concept building. And in the evening, I was playing. Now, this episode, my mom recalled, and I had forgotten yesterday. By the way, my mom sent best regards. And I was just butchering something like, I don't know, Bach or something like that. And then I think my mom told me that somebody asked, "Is there a Marco Bertola here?" And it was John, right? And they said, "Yeah, it's me," because he was in the committee for the postdocs, and he had noticed that, and so we started interacting serendipitously at that time. And it's hard to overstate the influence that John had on my career, my development, right? Because as it happened, right, I came to Montreal in '99 as a postdoc, and as is commonplace for many people after the PhD, you are a little bit lost, right? You've lost your supervisor, you need some extra new guidance. And for a while, I was a bit freewheeling, and it happened that also Bertola was there, as he recalled. And John, as is usual, is a catalyst of interaction between people. So we started talking in the room downstairs, and Bertrand was explaining this bioorthogonal polynomial, and we started interacting. And that actually was exactly one of my first interactions, right? And then out of that came my very first research paper, unconnected with my undergraduate. And we have our long collaboration, and we started exactly with this paper, right? In 2002, but we worked since 2001 on that. And then now I stayed around that area, right? The integrable system, orthogonal polynomials, random matrix model was all stimulated by the interaction with John and Bertrand, but in particular over the years with John. John also gave a graduate course on random matrices that I was attending, and actually, I remember I asked you some questions and you say, "That's an interesting and very excellent research topic." And I think this talk might actually be related somewhat with that comment that I made during your graduate course. Not last, I essentially, a little bit like Dima, I owe John my job, because after being 2 years as a postdoc here, there was an opening at Concordia. And I am not exactly sure how John did it, because it was kind of transparent to me. I only know that my postdoc morphed almost seamlessly into a position at Concordia. I don't think I was even interviewed, or was some miracle that you performed behind the scenes. I know that there were moving parts.
There was a diplomatic
exchange.
Dima, he was hired on in Canada a research chair, and there was another research chair, and so on. And then it was sort of a kind of war in terms of power and influence between the mathematical physics group.
John, remember that you're being recorded.
Yeah. Then recognition that someone who had a big role in that was at that time the leader of the number theory.
Hershey, right.
Hershey, they got a chair and we didn't. And Hershey said, "We owe you something. What do you want?" I said, "I want Marco."
And you got me. So I will be forever grateful, right? Because it's a little bit unconventional trajectory for a young postdoc to just essentially not apply. And that was great. And not only that, he was, okay, so here are some pictures, right, over the various years. So all these people are supposed to be here, almost all, right? Tamara was here virtually. Craig Tracy was invited but couldn't come. Here is Olivier Marchal. This is Sasha Orloff. And Olivier Marchal is also here. And then you see other people that probably, well, Misha is there, right? Yeah. And so many other, well, probably not so easy to recognize. Oh, this picture looks much better here. Okay. And then he was also, right, it's not just, he's not just job and work, it's also life and love, I would say, because he was the witness to my wedding. Actually, so see, this is actually, I had two weddings. One was the civil wedding in Montreal, and then there was the religious wedding in Poland. Right, and you may recognize, some of you may know this guy was the supervisor of my wife, Tarek Ali, and so here is John. And there is another person not in this picture, who was part of this conference, which is Bertrand Denard. Bertrand Denard is the guy taking the photo, right? This is his wife and his two children. So basically, we have been friends and colleagues and office neighbors for 22 years, right? And I am, and you have witnessed, I'm daily amazed at the energy and the curiosity that shines very brightly on everybody that interacts with him. Sometimes blindingly brightly, right? It's always an experience, and it's a lesson, because it is hard for me to imagine that I will maintain the same level of enthusiasm over such a long span of research. So thank you, John, for friendship, guidance, and support over the past years. Okay, so now for the actual talk, right? I didn't prepare many slides, as you can see. I'm slide 5 out of 19 because I was sure that there will be plenty of interactions. So anyway, so the isomonodromic deformation story actually is great that Dima started, right? Because much of the things that I'm going to say will pick up on exactly more or less where Dima left off. And so the whole story, you can reach it, right? So the overarching question that we were cogitating about for 20-something years is how to practically represent isomonodromic deformations as some kind of de-autonomizations of isospectral problems. In the case that Dima discussed of Schlesinger equations, simple Fuchsian singularities, it is obvious, right? You just look at it, you see. The problem arises exactly at the point where Dima didn't cross, which is when you have singularities in the differential equation of higher order. So now, and this is the L Dima that John was thinking when you were talking about the A. But so what we are considering now here is a phase space with a Poisson structure. There won't be any extension. Here is a old school. It's the phase space consisting of rational R by R matrices with poles of fixed degree, but the position of the pole is part of the phase space, right? So it's not a linear, not technically, it's not a linear space. It's just a collection of all these possible matrices with distinct poles of prescribed degree. Now, the indexing, you may be wondering why it's fancy, strange shift, is just because I want to label the index of the matrices according to the order of the pole of the differential equation. So the actual, secretly, the actual object of interest is not L of Z, but the one form L of Z, dz. So on this space, we have obvious coordinates, which are the matrix entries and the positions of these poles. And this is, as we discussed today, is a Poisson submanifold of an infinite dimensional Poisson space, which can be, it's not a linear submanifold, right? Because I'm allowing the position of the poles to move, but it's a submanifold of on the dual of the loop algebra of matrices in GLR. And the R matrix structure that was on the board, and maybe still on the board, on this Poisson space is this Lie Poisson structure, or constant Kirillov-Surriot, represented here in this form, which is slightly different than what Dima wrote, but it's a completely equivalent. Or if you are more index oriented, right, this is the Poisson bracket between two entries of the same matrix. In this business, you have to think of Z and W just as a parameters. So this formula is supposed to tell you what are the Poisson brackets between all the entries of these matrices and also the C's, which turn out, but it's not a given a priori, turn out to be Casimirs. And it is, how do you do that, right? So, for example, if I want the Poisson bracket between these LJs with two different powers, I look on this side, I look at the corresponding power Z to the L, Z to the K, W to the K. And on the other side, you notice that because it's the same, when Z is equal to W, this is zero, right? So this is actually a rational, on this side, you have a rational function of Z and W with exactly the same type of poles, right? And so you read off the same coefficient on the other side, and voila, you have the explicit expression. There is, of course, a much more abstract way of presenting in terms of R matrix structures on dual loop groups, but this is easier to explain for the index-oriented person. So now, here is exactly what Dima was discussing, right? So we have a Schlesinger system, only Fuchsian singularities. Many of the things I don't have to repeat because it's not exactly the same notation. I use L instead of A, but it's the same thing. So now, Dima wrote also this formula in the isomonodromic deformation of the Schlesinger system. One defines these expressions that are Hamiltonian. We can also explicitly write as a sum over mu different from mu of a trace of H mu H nu divided up to some sign that I may C nu minus C mu. L, right, yes, thanks. And also should be a bit above. Mm-hmm. Okay. Maybe just factor 2, but something of this tenor. Okay. So those are the Hamiltonian which enter in the definition of the isomonodromic tau function, the very first incarnation of isomonodromic tau function. For 4 singularities and R equal to 2, this is Paul-Levé 6. Okay. And the isomonodromic deformations take the following shape. So you can say, well, you can write the Isomonodromic deformation for the wave function and say that the derivative. Let me add here iso, the derivative with respect of C nu of psi is equal to V nu times psi, which by the zero curvature equation turns out to imply the following equation for the Lux matrix itself. Okay, and now here the gain is the following, that you see on there are two pieces in this formula. This commutator and this extra bit. Now, if I didn't have the extra bit here, this would be isospectral deformations, and that is the Garnier system. It's an autonomous equation. The C's, if I remove this term, I should also simply think of this not as the derivative with respect of C, but as the derivative with respect to some abstract parameter. The isomonodromic deformation comes when you identify this abstract parameter in the isospectral deformation of Garnier with precisely the position of the corresponding pole. But then, of course, the matrix L has an explicit dependence on the position of this pole, right? Because it's right there. So, in principle, right, you would expect that if, and that, so you keep in mind that it has an explicit expression. Now, the key thing is that these two pieces have separate meaning, right? So the first piece is an isospectral deformation, and it's actually the Hamiltonian flow generated precisely by the Hamiltonian H. H is a scalar function of L. You take the Poisson bracket with each of the entries of L, and after a little bit of a computation, comes out that the output is precisely this commutator with this matrix, which I don't know, V nu, which is just the singular part of L at the pole C nu. Now, this extra bit is just coming out of the zero curvature equation. If the world is kind, right, you would have to think, okay, but are these the Hamiltonian equation for a time-dependent observable? Well, yes, as if this extra piece is precisely the explicit, quote unquote, derivative of L with respect to the position of the pole. And it turns out that indeed it is, right? It's just, this is pure calculus exercise. So indeed, now you can represent, okay, sorry. So, so you can think of these equations here, right, as a time-dependent Hamiltonian equations of the form derivative with respect of C nu. Let me add here iso, right? Because to distinguish the derivative, the isomonodromic derivative, so the derivative which preserves the monodromic representation, distinguish it from the explicit derivative where you think of these C's and these L just as independent.
May I ask, why don't you write extra derivative with respect to the C nu? It's the same, I see.
When L changes, it changes in two ways. One is the entries in the matrix change.
And also the position. Right, so that's the
also the explicit C.
So this is the explicit derivative, right? The naive, let me call it naive. But it is, in principle, is a complete accident that this piece here, which comes from the zero curvature equation of Schlesinger, is also the explicit derivative of L.
It was an accident.
Well, yes.
It's
not, yeah.
In 1995, it was an accident, it didn't work.
It's an happy accident, as
Yeah, but it's a theory.
no, of course it's also here is a theory because it's a computation. But no, the point of this talk is precisely to flesh out this idea in the case where the analog of this identity is not obvious at all. Okay, and I will be back in a second to that. So what we are writing is that this isomonodromic isom, right? Because there's also isospectral the derivative is equal to the Hamiltonian vector field, so the commutator of, I always forget on which side we have to put, but plus the explicit derivative, right? So stick here L, okay.
Then 0.
Put a naive. Okay, right. So that is now you've recognized that L is just some time-dependent function, and this is exactly the way a time-dependent function evolves under Hamiltonian flow, where the Hamiltonian also depends on time. Okay, so now we go to the general case. I'm not going to the fully general just because there are many indices. I don't want to deal with it. So let's take the simplest of cases where L is just a polynomial matrix of size R. So the minus is just notations. Now, the only condition is that, so these matrices L0, L1, etc., are just some arbitrary matrices. The leading coefficient is supposed to be diagonal with distinct eigenvalues. That's it. That's our phase space, right? In this case, the phase space is just a bunch of matrices. There are no positional poles. It's a simplified expression. Now, Bertrand in his talk briefly mentioned that when you solve the differential equation psi prime equal to L psi, right? We have here a singularity, irregular singularity in the ODE with Poincaré rank D at infinity. And in general, the asymptotic behavior, there is no analytic solution at infinity, but there is a formal solution that you can write down. This is the psi formal, and it has the following general shape. So we have a prefactor, which is a series in 1/z. So it's formally analytic because it's not convergent. So formally analytic at infinity. So it's okay, you can think of it as an analytic series, but it's not convergent. And then there is this exponential, which has the essential singularity type. And this T is a diagonal matrix. I denote by this factor H, the Cartan subalgebra of GLN, so the diagonal matrices. Right? Each of these matrices is a diagonal, including T0. And these T1 up to the game will be played with respect to the entries of these matrices. And these will be, we'll call them the higher Birkhoff invariants. These things are considered to be constants in the game that we are playing, and they are called the exponents of formal monodromy.
So the log.
The T0, right? Monodromy. So Bertrand actually discussed this in his talk. So the parameters, the isomonodromic parameters, are the entries of each of these matrices, but this T0 plays a role, is a spectator in this game. Okay. All right. So what are the let me remind you of the definition of this monodromic functions so that I can introduce the quote unquote Hamiltonian, but so far is an unwarranted name of Hamiltonian because it isn't clear whether they are Hamiltonian generating anything here, right? But let's call them H. So this is the formula that the Japanese school in the 80s proposed for the isomonodromic tau function, and the implicit statement here is that if the Lux matrix deforms in such a way that the generalized isomonodromy, which means the Stokes matrices, remain constant under the change of the Birkhoff parameters T1 through TD, then these derivatives satisfy the, if you take a cross derivative, they are equal, so they define a bona fide closed differential, and you call that the differential of the logarithm of the tau function. So in other words, there exists, if I take dtkb of that, I can swap the order. Okay, so it's an implicit statement of this fact. And the isomonodromic equation, they look on the prima facie, they look exactly the same as for Schlesinger, except that the matrix that appears in front of the deformation, so that was before a V, is now a polynomial matrix defined by this formula. So let's parse this formula. You take your Birkhoff exponent, right? So remember that T is T d Z to the D, etc. T0, T1 Z plus T0 log Z. And you differentiate it with respect to one of the higher Birkhoff invariants, which explicitly just gives you this elementary matrix, diagonal matrix multiplied by the power. You sandwich with this formal series, formally analytic series, which has only inverse powers of Z. And then you project onto the polynomial part. The result is a polynomial, right, of degree J. And the statement is that if the psi solves this equation, then by the Stokes matrices remain constant. And as a consequence of the zero curvature equations, you get these isomonodromic deformations of the Lax matrix. Okay, so same general structure as before. So you define the isomonodromic deformation of L as the effect, as an infinitesimal deformation defined by the right-hand side of this equation, right? So here you have again a commutator and some extra bit. Now, before this extra bit happened serendipitously to coincide with the naive explicit derivative of L with respect to the position of the pole. But now, if you look at L is an unstructured matrix. There is no obvious way in which you can identify the times, these isomonodromic times, inside that matrix, right? So you can't say naive. What does it mean naive? Where are the T's in my matrix? I only have matrix entries floating around. And so that's the problem that we are trying to address. In which sense this thing is the naive derivative of L with respect to this isomonodromic time? Or even does it make sense to think of that as a naive derivative? So those are the big questions. Okay. Now, first big question, well, maybe not so big, right? Is in the folklore of the business and it's actually not in the folklore, is in the literature. That this part here is, of course, an isospectral deformation, exactly as before, right? And is this a Hamiltonian vector field? Yes. Okay. Is that exactly the Hamiltonian vector field for the Hamiltonian Hj, which was written before? And let me just cut and paste here. Okay, for this Hamiltonian, right? So, in other words, if I take the Poisson bracket, the same Poisson bracket, the constant Kirillov-Surviot, etc., Hja, this is a scalar, right? With each of the entries of the matrix Lz, compute, out of the computation come the commutator of precisely that matrix Uja with L. And let me paste also this part, right? Because, come on.
Within a sign.
I think, yeah, I never remember if the Hamiltonian goes first.
Only in those seconds.
Okay, yeah, so modulo science, modulus. Okay, all right, so that's a theorem. I mean, it's not a surprising theorem for people that are floating in this business. Let's call it even exercise, right? So you just have to check, you know, the Hamiltonian, it's in that. But it's yeah. Oh, sorry.
K can be 0 as well?
No, sorry, K goes from 1 to D. Because 0 are the exponent of formal monodromy, and those are not allowed to vary. Okay. Now, and then again, the big question, right? What is that? Can we think of it as the explicit derivative of L with respect to the time? It's unclear, right? Because it carries the indices J and A, but so what? So how do you know, what does it mean that it's the explicit derivative? There was no T, as we discussed. Okay, so let me give a definition to that term, right? So that I can handily refer to it. I'm going to toss around a few big words. And now, I expect some interruption, but I will call this piece the Birkhoff connection. Nabla, let's define. So what? So we think of. So you have your space of Lax matrices L, right? And out of the computation which you can do by linear algebra, on this space you have these Birkhoff invariants, higher Birkhoff invariants, right? Which you can think of, so you out of L, there is a procedure I can tell you if you need to know, but there is a procedure how to compute those T's. So you think of those T's as functions of Lax matrix as they are. They are functions of L. So now take the projection given by the computation of these Birkhoffs. Let's call this space T, this curly T, right? This is the manifold, the very simple manifold consisting of D diagonal matrices. Why did it do that? Okay, D1. D diagonal matrices. This one is to be with distinct eigenvalues, but okay, D diagonal matrices. So you have the computation gives you a fibration, which actually a little exercise. So theorem is a regular fibration, the fiber are all the same dimension, etc. And then I can take any tangent vector on this space, and I think of this nabla as the connection, right, of the Ehresmann, if you want to know, but some kind of a connection that lifts the tangent bundle of T onto the tangent bundle of L. By what? In which way? Just by this formula. You declare that this expression, the extra bit in our isomonodromic deformation, is expressing the action of some vector field on L. Okay, so
the point that some people will say all of the T's are Casimir invariants.
They will turn out, yes.
So it's a projection to almost all Casimirs. If it were all the Casimirs divided into this.
Actually, in this particular example, they are exactly all the Casimirs. So in general, yeah. T0 is not a Casimir here. Yeah. Right. So you, as John said, turns out, spoiler alert, these T's are also the Casimirs, precisely the period Casimirs of that Poisson structure. So in fact, the fibers are precisely the symplectic leaves. It's not exactly true in the general case, but morally true in the general case. Okay. All right.
There's not really a bundle because there could be different strata.
No, that the theorem is that the strata are all same dimensions. It's an honest vibration here. And the reason it's honest is because this thing has distinct eigenvalue. So that you have a bona fide connection, right? And then you would like, so now I can write my isomonodromic equations. Well, but it's pure semantics here so far. So this is the Hamiltonian vector field. Probably I got the order wrong. And this is this other connection. Now, do I have the right of thinking of this thing as the explicit derivative with respect to T? Well, for one, if just to have the right to do that, they should commute, right? Because this thing, they commute between themselves. So in other words, you have to prove that this connection is flat. Otherwise, you can define whatever you want. So the big picture is empty, probably in the interest of time, I will leave it as you see the big picture. Okay. This is a big picture, and I leave it to the imagination. But well, we have the space L, right? And then there is this vibration onto the space T, that are the Casimirs, right? And the fibers of this vibration are precisely a symplectic leaf. So the Hamiltonian vector fields are tangent, of course, or they're tangent to the symplectic leaves because those are Hamiltonian vector fields. They can't do anything, right? It's a Poisson vector field. But this extra bit, this lift of the tangent, it better be transversal. Right? And that's exactly, so you should prove in particular that this transversality holds and so on. So that's the general picture, but even better, you have to prove that this connection is flat. Otherwise, you can't think of these things as explicit derivatives. So now let's come to the results because time is running. And okay, so well, the first result is this part that, if you wish, is an elaborate exercise. Okay, so the Hamiltonians, or Hj, they come from the tau function, are first result, they are spectral invariant. That is not obvious, not immediately obvious at least, from their definition, right? It's unclear whether, sorry, let me show you the definition, right? If this number can be expressed as something relating to the spectrum of the matrix L, the spectral curve. But the statement is true. Okay, so that's the first. And second statement is that exactly as for Schlesinger, if you take the Poisson bracket, and also I already said a couple of minutes ago, the Poisson bracket is precisely the commutator between those things. So what does it mean, spectral invariant? Well, it simply means that you look at the spectral curve, the fancy word for the characteristic polynomial. Okay, so it's a polynomial of degree R with respect to the spectral parameter lambda. You should technically compactify. So think of these spectral curve as R branches, and you have to add R points above the point at infinity. And so in other words, when Z goes to infinity, your R branches of the spectral curve, right, lambda to the R plus minus trace of L of Z, lambda to the R minus 1, etc., right? And then it ends with the determinant with some sign. Okay, when R goes to infinity, our assumptions imply that the R different branches, let me denote them by lambda A1 through R, they are just some low rank, well, some series in Z with a, well, it's written where it's written here, right? They looked at this. So they start with the power Z to the D minus 1 because L is a polynomial of degree D minus 1. And they have only integer powers. The fact that they're integer powers is precisely. There's no CA.
Oh, I'm sorry. No, you're right.
Yeah. Okay, so there's just this polynomial part, and these pieces here are precisely, so the statement implied by this formula is that if you take the Taylor expansion of your branches of lambda, these coefficients are exactly at this one, the Birkhoff invariance, higher, two, they are Casimirs. The fact they are Casimirs is the general theory of the rational R matrix. Okay. And also here you find in this pivot position kind here, you find the exponent of formal monodromy. They are not Casimirs, by the way, but a separate story here. And then you continue the expansion, you will find precisely the Hamiltonian. In that sense, these Hamiltonian are spectral invariants. And notice that this TDA is kind of paired, oops, sorry. It's paired with this thing. Right, so it's some kind of duality implied by the formula. The next one, this one is paired with that, right? And so on and so forth. They are symmetrically placed around the pivot of this expansion. So what does it mean? If you were doing isospectral, you could say, forget the T's, those are parameters. Take the flow generators by one of those are just isospectral deformations. They flow linearly in the Jacobian of the spectral curve, very nice, etc. Now, I have an infinite choice of Hamiltonian, spectral Hamiltonian I can use to do my isospectral. Okay, no, not a good idea. Now, please type if you can hear me, but I will not be able to hear you if you speak for the moment. I guess not. Well, oh, we hear you now. Okay, great. Okay, thanks. Okay. All right. So, but if you want, okay, if you want to say something, just put it in the chat and then we will unmute. All right. So, what was I saying? Oh, yes, they commute. In other words, this connection is flat. Okay, put it in a more geometric way. Moreover, it's not entirely clear, but it is in the cards, in the deck of cards of Alberto, that it's in that deck of cards that if I take remember that these T, this Birkhoff invariants, you should think of them as just functions as they are on the phase space. Now, if I want to think of my nablas as explicit derivatives, it should be that they exactly do as you expect. Namely, if I take the list of the vector field D derivative respect to Tja and apply it to the function TKL, it should be delta Kj, delta La, right? So that's part of the theorem again. So it's a verification, right? Consistency. The other part comes as a bonus, if you wish, is that this connection actually preserves the Poisson structure. So it's also the Lie derivative with respect to this Poisson structure is, the Lie derivative of the Poisson structure, the constant Kirillov-Souviot, or R matrix structure with respect to this nabla, is any of these vectors nabla is zero. And either, in other words, you have this equation, right? And then some geometric consistency verification is that you need to verify that this nabla connection is always transversal to the symplectic leaves. That's also okay. Not only it's transversal, but it's also of constant rank. which is also important because if you have a distribution, which by the formula is integrable, right? It's even better than integrable. If you have a distribution and it is a constant rank, then you can take the quotient, and that's essentially it is essential for the next step. So the consequence is that you now imagine that we can find a full set of invariant nabla invariant functions. So functions that are annihilated by these vector fields in nabla. Let's call them W1, Wk. What is K? We have to count, right? Is the dimension of this symplectic field. So this W is in Poisson's value precisely because nabla is Poisson, right? So in other words, the nabla of the Poisson bracket, you can actually write. Oh no, sorry. Okay. The nabla of the Poisson bracket is 0. So in other words, the Poisson tensor in this coordinate would be time independent. Okay, so you split completely the Casimirs from the coordinate. And so you can think of this W as parametrizing, honestly, the symplectic, in a universal way, all the symplectic leaf. And in other words, you are now realizing that L, at least locally, right, this the phase space is a Cartesian product of these, the manifold parameterized by these W's and the Casimir. So it's a Cartesian product, and the Poisson structure here is just a trivial one, and the Poisson structure knows on W does not know anything about T, right? Because it's 0. Okay, so it's a complete direct product of Poisson manifold, one of which is totally trivial. And so if you now express your isomonodromic deformations in this set of coordinates rather than the naive one, namely the entries of L, you get a Hamiltonian system, which is just with some time-dependent Hamiltonian, right? W is not time-dependent, but the Hamiltonian is time-dependent. Okay, so now the questions is, now the open problems. How do you construct this set of W's? We don't know. Okay, in the explicit example, you take Maple or Maxima or I don't know Maxima, but so you just you write down explicitly the vectors of nabla and ask Maple. Maple can do that. Find me the invariance, and it spits out the formula. Okay, okay, but then you look at it and do some computation, some muscular exercise. There are only few cases in which this has been done, not phrased in this way, but implicitly doing this procedure. First is a paper of John, right, which he did in the for Painlevé equations. And we realized that the Painlevé equation are the sort of time-dependent version of the paper, right? The Adams, Hurtubise, Harnad-Hurtubise.
Before the duality, which is one irregular singularity and infinity of function of
one. Okay. So that also that include okay. All right. So stand. Now there is also another result that I want to mention due to Marta Mazzocco and Mo Manyu. Manyu Mo, that they essentially do what we would like to do, not phrased in this way. They didn't introduce this Birkhoff connection in the same terminology, right? But essentially they constructed a collection of coordinates that are turned out to be nabla invariant, coordinates in which the Hamiltonian equation just become the Isomonodromic equation just become Hamiltonians with Hamilton with the time-dependent Hamiltonian for a particular class of Lax matrices with one simple pole at 0 and an irregular singularity infinity subject to 2 by 2, or it's written there 2 by 2 with this type of symmetry, which is it's known in the literature as the Painlevé 2 hierarchy, generalizing the Flaschke-Newell Painlevé 2 Lax matrix. But in general, even for just polynomial SL2 matrices, we do not have a procedure, but we have an example, so we can work out example, and it doesn't look ugly at all, right? It's completely explicit. So this is, you take a polynomial of degree 3, degree 2 would be not interesting, well, I mean, interesting, but it's Van Leeuwen 2. So the next step, right? Polynomial degree 3. This is a general matrix. Now I can get parse. Sigma 3 is sigma 3 Pauli, sigma plus and sigma minus are also upper and lower triangular matrices. And out of like an explicit computation, right, with maxima, you get out a parameterization of this matrix where now the T appears explicitly. Right? So what this formula is telling secretly behind the scene is that these coordinate X, Y, and Z, they're actually precisely incarnations of those nabla invariants that I was discussing a few minutes ago. Okay, so not only that, they've been massaged so that they are not just nabla invariant, but they're also W in the obvious sense. And then you can simplify because there's also the action of the translation and validation. So you essentially can kill T3 and T4, and it takes a little bit nicer form, but this is an exercise, right? And here you have the isomonodromic matrix, the matrices of the isomonodromic deformations of this simplified thing, right? They take a simple form, and indeed, which is just a verification, cherry on the cake, you have precisely what we wanted to obtain in the beginning. So this is the one line that was the explicit. Now, in this parameterization, the nabla becomes the naive differentiation with respect to T. And the naive differentiation with respect to T corresponds to the C derivative of one or the other, which one we are looking at. And so that's basically all I wanted to say. And now to keep with many of other people, and many other speakers in the conference, I wish to conclude with an happy birthday for John. And here is actually a photo of John in, I think it was Banff, 2000, can you read it here, right? So it's Banff 2010. So thank you for your attention.
Right, John. So you wrote down this tau function.
Sorry, like also. Okay, let's see. Okay, well,
You wrote down this tau function. Or is just one function?
the tau function is a scalar function of times. Right. Sorry, it's the Jimbo Miwa, the original one. No fancy business there.
Yeah, I think it's.
Maybe I forgot the trace somewhere. No,
No, it is
I
okay.
put the trace. Yeah.
But at some point you wrote this TJUM or something, or a bit further on, I guess.
JMU, it means Jimbo Miwa.
Oh, but okay.
No.
But it's okay. Yeah. And another question: how do the variables T0 come in?
So that would tie in with the question in the previous talk, because T0 is not isomonodromic dependence. So you cannot write isomonodromic deformations in this way.
Yes.
So then you're asking how does this tau depend on the monodromic parameter?
Yes.
That's different question, which we partially address, actually, I should say, in a paper with my students of Pietà Icone, where we actually constructed, in the spirit of what Dina was doing, a coordinate on the wild character value, on the Stokes matrices, for two by two polynomial matrices. And so, in principle, out of the same logic, we take UV form on one side minus UV form in terms of Cockcruncher. On the other side, you get the dependence.
Let me say something. First of all, Marco is focused on polynomial case, but it was the same sort of. But there's a difference. These exponents of Isomonodromic and infinity
Mhm.
are not Cassimers. The ones that find that points are Cassimers. So they're just technically, so they're not only Casimir, but they play no role in this.
Let's see.
Just the ones at infinity, which are not Casimir, generate a beautiful
Okay,
group.
does it work? Okay.
Which is not one of the Isomonodromic equations,
Mhm.
but it's a symmetry. It's a group. It's an R-dimensional group of symmetries, and it's exact. They generate, as Hamiltonian flows, the group of conjugation by constant diagonal matrices. And so you can write that down. The DLD, whatever, DT0 is a common, but purely a common. There's no added term. It's just really a nice spectrum.
The answer to that's practically. Just because implicitly, this is a moduli space with a decoration, extra decoration, frame. That's.
Any other question?
Any questions from the remote audience? Assuming you can hear me.
I don't know if there's a question from. Oh, hello, Claudia. Yeah. Yeah, okay.
Okay, let me ask now.
Yes, that doesn't look like there's an.
Okay, in that case, John, would you like to,
This is just to finish.
finish that?
So there have been so many eulogious remarks made, and I would like to also give some. Oh, you can.
Yeah, but.
The others can.
This one should be working.
Okay. Claudia, do you hear me? No. Okay, okay. So this will be very brief because everyone's tired. I'm tired. It's over. But first of all, Marco gave these wonderful reminiscences of sometimes, and others have done the same. I'd like to, just with regard to Marco, say a little bit more, 3 minutes more. Keep me to 3 minutes. And then I would like to thank everybody for having taken the trouble to come here and to participate. And this really was a wonderful event. Prior to our hiring Marco back in whatever 2000 or something, of course, we were at the MSRI together. And I remember two significant events, well, three, which brought me in contact with Marco. One was, he was a graduate student. He was totally mistreated by MSRI. He wasn't given an office. He had to work in the computer room. And I don't think he was completely happy about that, but the program was very interesting.
I was a student.
Yeah, okay, but one thing which happened, he was always like he does now, very athletic and sporty, and he was going around with his bicycle. So before I say the bicycle incident, I have to say that we did discuss things. I found out from him about his thesis, which was fantastic. He wrote a fantastic thesis with Boris Dubrovin, which was a beautiful class of solutions to the Frobenius manifold equations. Yeah, but it's memories, joint memories. And anyway, so this was a wonderful class which made a hybrid of elliptic functions and modular functions. So what were they called? Jacobi forms. And so he told me about that. I was totally bedazzled by the beauty of this and the generality of the construction. So that was the actual scientific starting point. Then once, I don't know, it was at Berkeley and in front of Alberto's building. What's the name of the building?
Evans.
In front of Evans is the bus stop where the bus from the MSRI comes down. But of course, Marco wouldn't take the bus. He had to take the bicycle fast, going down that very steep hill. And we agreed to meet at the bus stop. And I couldn't believe what came in front of my eyes while I was waiting for Marco to arrive. I think we had a meeting or maybe some. This whirlwind bicyclist came and did not come to a screeching halt. He did a somersault forward.
Now you were better. I fell before, but
Okay.
it was so broad.
What I saw was a somersault. I don't know. I saw the bicycle go up in the air and come around, and then you covered with injuries, and we had to get some emergency something and patch you together again. And that was our real first meeting. Boy, was that a dramatic one. Okay. So, yeah, well, I'm finished with the Marco. I mean, I just wanted to supplement that. And again, to everybody, I just want to give my heartfelt thanks and appreciation that you've all gone to so much trouble to celebrate to celebrate our long-standing interactions and the science that we have now. So thank you very much.